can see why, because that's on. I'm going to turn this projector off. I'm going to have to ask you guys, I think, for values. So we're going to put the 5-number summary onto this axis. I like the fact, Carly, that the dot plot is already there, because it's going to give us an idea of your variation, your range you were just talking about. Our minimum value was 4, yes? Right here. So what you do, if you want to add a box plot to this guy, is just put a little vertical line above that. You can put it right on the axis too. If you guys want to draw this one along, just sketch out a real quick horizontal axis, and then you don't have to put 1 through 50. You can go like 5, 10, 15, 20. That'll get the job done. And you put a corresponding one of those above your maximum data point, above your maximum, which in this case was the 43 out here. What's the distance between those two? 39 states. Remember what we used to call that way back in the day? You guys invented this way back in the day. It starts with an R. We call that the range of the data. Very, very nice. Very, very nice. We haven't talked about it much since. That's okay. It's all right. Not a whole lot of reason to, and you'll see why momentarily. Now what you do is you go back into your data and you put slightly larger vertical lines on the quartiles. 10.5, I think, was Q1, yes? Yeah. That's right here. Man, that thing is shaking, isn't it? And I looked directly into it. That was brilliant. And Q3 was 22.5. 22.5. Thank you, guys. 22.5. And then you draw a box between those two. And while you're at it, slap one more vertical line on the median, which was 14. 14. So what you have is you've got a box around the 2 middle 25% regions. And then here come your whiskers, Pat, you were asking about. Those are your whiskers. So you get a box of whiskers. What you've done is you've taken your data set, you've indicated the 5 numbers in the summary, the min, or Q0, Q1, median, Q3, and then your max out there, and your max is out there. But you've done it in a graphical way that not only gives us the values, but also shows what Carly just said. Remember what she said? She said the data in the upper 25% is more varied than the data in the next down 25%, which is more varied than the data in the first 25%, which is more varied than the data in this 25% right here. And you can tell the variation because, graphically, say that again, Vivica. How long that section is. The longer, this is why I love having the dot plot with it. You see the clusters? Where the clusters are, the box is very small. Because we had 29 people in our sample, right? So that means we've got roughly 8 data points in each of the quarters. 8, 8, 8, or 7, 7, I guess. 7, 7, 7, 7 is 28. That's almost 29. So there should be about 7 points in each quarter. It won't always be pretty, sorry, traditional math students. It's not always exactly equal to blah, blah, blah. Like the median here is exactly 1 point, go to the middle. But look at, count them up. 1, 2, 3, 4, 5, 6, 7. Okay, right there. There's your first quartile, dividing the low from the next up. Then you got 1, 2, 3, 4, 5, 6, 7. Here's your next quarter. Notice these guys are more spread out than these guys. Therefore, you get spread here more than you get spread here. Next 7, 1, 2, 3, 4, 5, 6, 7, somewhere in here. And then your last 7, 1, 2, 3, 4, 5, 6, 7. All over the place. All over the place. So you get, for free, a visual look at variation without forcing the standard deviation measure that might be misleading. So you get an idea of how spread out things are without having to introduce some arbitrary, somewhat arbitrary, or somewhat, I shouldn't say arbitrary, somewhat forced value that might be misleading. Some box plots will also slap the average on there. They'll make like a symbol like a triangle or something and put it like right, I think our average was 17, yeah? And they'll put that like right there and say there's your average too. I don't care for it particularly because, well, first of all, if not everybody knows what it is, they're going to wonder what it is. And number 2, it's mixing and matching. It's forcing center where it might be skewed into. The only thing I can see it might be a benefit is to prove to you that you've got skewed data. And the further apart, the further this guy gets from median, the more skewed it is. So sometimes you'll see the average in there, most times you won't. Ask me questions about this. Concerns, comments, questions. It is fairly straightforward, yes. Fairly straightforward. Fairly straightforward, yeah. It's nice because it gives you the visual. And what you're about to see, where it collects the data after the break with this Ben Snowfall day, some random sampling exercises, it's really nice when you're comparing data sets to use these things. I helped, you got any rock climbers in here? Rather, I know you are. Got a couple rock climbers. Entrepreneur company in town, they make climbing holds. And about 9 or 10 years ago, they wanted to change their resin that they use in the holds. When they make climbing holds, they're horribly toxic. I mean, the chemicals they use, they wear these crazy like hazmat suits to make them. It's awful. And they were trying to go more eco with the chemicals, but they were worried that if they went more eco, the holds would get weaker. So they had a bunch of like prototype, whatever, alloys, not alloys, what's the word I'm looking for, mixtures of the resins, and they had old holds from the old stuff. They did a bunch of stress tests. And they said, what can you tell from this, from the results? What they would do is they'd put a weight, and they'd increase the weight, and they'd pull down the hold until it snapped. Originally, it would crack once, and then they'd keep pulling until it failed completely. And they had different kinds of holds. Some holds obviously are shaped different. There's ones with big holes in them that you could get a hook on. And there's some that are really tiny that you couldn't do that on. And they had a whole standard breadth of the entire shapes, like rosin 1, rosin 2, rosin 3, rosin 4, and then the control rosin. And what I learned, and I used box plots to do this, at least to get my initial analysis, was that the new rosins were cracking sooner than the old rosins would, but once they were cracked, they would hold longer than the old one when it was cracked. Does that make sense? So it would crack sooner, but it would also withstand more force than the old one once it was cracked. But that wasn't good enough because they don't want to sell holds that are going to crack more quickly. Because as soon as something cracks at the gym, they're going to pull it down and throw it away. They're not going to wait till somebody falls 20 feet and breaks their neck. Oh, I'm sorry, waited too long. No, you don't do that. So, but the thing was I couldn't tell that from the numbers. I had this spreadsheet full of numbers, and I'm like, nah. But what I did was I just slapped up a bunch of box plots, and one of the box plots rose below, and then the other ones rose above the rest. And I'm like, aha, there's a difference. Let's analyze that now. And that's where this comes in handy. You'll see why here momentarily when we regroup after our break and start talking about comparative box plots. But you're right. It's pretty straightforward, Veronica. Go ahead.
So you said we can use this method for any type of data.
Any data set
so
you
why
want.
would we go back and use the other?
Fantastic question. Why would you go back and use? How long an answer do you want? Give me minutes. How many minutes do you want an answer? 2 minutes?
Quick.
Quick answer. Okay. The question is, if this works all the time, why do we ever use the other? Back 3 weeks ago, we learned that the mode is always reliable on any data set. Even when the average and maybe the median aren't, you can always use the mode. Why don't we use the mode all the time then?
Not as fine.
It's not as, can I take the ite off of there and say not as fine? We get more detail with an average. You still have the loss of detail because you're dealing with percentages. So for example, if I turn this dot plot off, and all you have is the box plot, now you don't know where the data lie inside. You know that there's more variance here than here, but you don't know where the actual data lie. Do they lie like this? Are they like that? Or are they like this? Are they like this? You still lack a little bit of detail that you would not lack with an average. But the trade-off is you can use this, so you get something. And something is better than nothing statistically as long as you use it properly. Is that a fair enough answer? Yeah, that's a great question. If this always works, why not always use it? I'm not saying you can't always use it. When you come back, we'll show you how to put the dot plot or the box plot on top of the histogram at the same time in your TI. And you can get a visual of both of them at the same time, which is kind of slick. I mean, it's kind of nice to see both. It's kind of like seeing this up here. So that's the best answer, is when you can't have the perfect world of the average, which the average is wonderful because it gives you that level of detail. At least you have this. It's a nice fallback. It was almost 2 minutes. I actually got the timer now. Speaking of 2 minutes, let's take 5. And then come back and we'll collect some data, do some more analysis. Great question. Thank you. Fantastic question. A lot of times it's just a first look too. I mean, even if you don't know your data is or isn't bell-shaped, take a look at it.